Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are almost nearing the end of the 6th week, and we have already looked at adaptive control design for a first order scalar system, and we are well into the discussion of looking at adaptive control design for second order scalar systems. And the rather cool thing is that a lot of mechanical systems, including the spacecraft by SpaceX that you see in the background orbiting the Earth, fall into the category of systems that can be modeled by some kind of nonlinear second order systems. Right? And so what we are already looking at in the 6th week of this course will very much be useful to design algorithms and develop controllers in order to sort of control autonomously or drive autonomously systems such as what you see in a background. So this is where we were last time, and what we had realized was that for the second order system, we sort of hit a detectability obstacle because we started with a non-strict Lyapunov function for the known system case. Yeah. And what it meant was that we could not even prove that the position error in fact converges to zero. All right. So one of the solutions that was, well, one of the obvious solutions is to obviously construct a strict Lyapunov function, which may not always be easy. However, that's definitely one viable choice. However, one of the, in fact, more simple solutions was this Ortega construction, right, which was proposed by Romeo Ortega in the 90s. And this is, he in fact proposed a function which was not even a Lyapunov function. So it was like a Lyapunov-like function. And we are starting to look at it from in the context of this simple spring mass damper system. It's not the the error system, but the spring mass damper system. And there is no parameter either. There is no parameter error either here. And the aim is to drive x1, x2 to 0 as t goes to infinity. And the choice that he proposed was basically something like this: half x2 plus alpha x1 squared. And we know that this is only positive semi-definite because v at k comma minus alpha k is 0 for all values of k. Therefore, in fact, along a straight line, along a particular straight line, this function is 0 arbitrarily close to the origin also. And therefore, this is not a positive definite function as per our definition, and hence not a Lyapunov candidate either. Right? Great. So how do we use this? So this is where we are today. So this is say lecture 6.6. This is where we are. So how do we do? How do we use it? So we take the derivative of this v, and that's x2 plus alpha x1 times x2 dot plus alpha x1 dot. And I simply substitute for the derivatives from our dynamics. So x1 dot is of course x2, so it goes like this. And x2 dot was minus k1 x1 minus k2 x2, which is the standard spring mass damper sort of dynamics. What do we do after that? We sort of club the x2 terms, which is minus k2 minus alpha, and we pull that out here. Okay, so what are we left with? This is retained as it is. Since minus k2 minus alpha is pulled out, the scaling on x2 is identity now. And the scaling on this guy becomes k1 over k2 minus alpha. This is what we have. Now, if we make a choice of k2 such that it is greater than alpha, and I'm allowed to because it's a spring mass damper. If I'm trying to stabilize, I can choose K2 to be anything I want. So if I choose K2 to be greater than alpha, and alpha is also something that I choose. So I have a lot of things that I can tweak. And also I choose alpha such that that is exactly equal to this quantity. Exactly equal to this quantity here, which of course give me some, so because this becomes a quadratic equation in alpha, so I get a viable solution here. Right? So if this quantity becomes alpha, you see that this whole quantity becomes x2 plus alpha x1 whole square. Okay? And that's what we write here, x2 plus alpha x1 whole square. On top of that, I've already put in the requirement that K2 is greater than alpha. So this quantity is strictly positive. Therefore, this entire quantity is negative semi-definite. Right? Great. The other cool thing to see is that this exactly looks like the V. So in fact, this is twice of V. Yeah, twice of the V function that we chose. So that's what I do, that I substitute x2 plus alpha x1 square as twice V. Right? And I can see that V is of course a scalar value quantity. So I can see that this is a nice exponential decay in V. Right? There's a nice exponential decay. In fact, I can even solve this. I can even solve this to say that Vt is V0 e to the power minus 2 K2 minus alpha t. And in terms of x2 plus alpha x1, also I can say that yeah. So two things happen. One is that this is V is actually half squared of this, and V0 is half squared of this. So the halves cancel out, and then I take a square root. So therefore the 2 goes away here. So that is essentially the exponential decay of V, and therefore the exponential decay of x2 plus alpha x. And of course, alpha is also positive quantity. Right? So this is what we have. This is what we have. So, great. So great. So now we do a little bit of signal chasing type analysis. The steps are slightly different here. Yeah. But they still work out fine. Yeah. So the first thing is V is still lower bounded because V is greater than equal to 0. And it is non-increasing because V dot is less than equal to 0. Right? I mean, even though V is not a Lyapunov candidate, I still have both of these. Yeah, that it's lower bounded and it is non-increasing. Therefore, V infinity exists and is finite. Right? V exists plus finite. Right? And then V infinity is what we use to denote this limit of V as t goes to infinity. Okay. So further, because V is x2 plus alpha x1 squared, we know that this is a bounded quantity. Yeah. We can also show that x2 plus alpha x1 is in L2. Right? And x2 dot plus alpha x1 dot is in L2. In fact, this step is, I would say, not required because we have already proved that x2 plus alpha x1 goes to 0 as t goes to infinity. Yeah. So we don't need this. Don't need this step. This can already be claimed from this can already be claimed from your exponential decay of V. Yeah, we already did this, right? Because you can see this is the formula for x2 plus alpha x1 at time t. So if I take limit as t goes to infinity on both sides, this guy is going to 0. Right? So x2 plus alpha x1 is going to 0. So what do we know? We know two things. x2 plus alpha x1 is a bounded signal. So let me call this some phi of t defined as that. And I know that limit as t goes to infinity, phi of t is 0. Okay, sorry, not phi of t. I've already called it p of t later on. So p of t is defined as this, and limit as t goes to infinity, p of t is 0. So I know these two things. Okay, right? I know these two things. I know further that x2 is equal to x1 dot. So I can rewrite p as also x1 dot plus alpha x. Okay. So what do? We now apply the Laplace transform on both sides and do a little bit of rearranging of terms. So how do I do that? Laplace transform here gives me ps, and here I get sx1 minus x10 and alpha x1s, which goes to the other side to become minus alpha x1s. Okay. Now, in order to compute x1s, I combine these two, and I get x1s as x10 over s plus alpha and ps over s plus alpha, just by rearranging and manipulating terms. Now, if I apply the final value theorem, in order to apply the final value theorem, what is it? I know that final value theorem says that limit as t goes to infinity, x of t is basically equal to limit as s goes to 0, s xs. Okay, and that's what we do. Right? So I multiply s on both sides and take limit as s goes to 0. So I get from the left hand side, I get limit as s goes to 0, sx1s, which is actually this quantity. Yeah. And further, and of course, I can, on the right hand side, I have this guy. Now, what do I know about this? I also know that p goes to 0 as t goes to infinity. So from here, I immediately have that, again by the final value theorem, that limit as s goes to 0, s times p of s is 0. All right, great. Now notice, this is what is there here in the numerator. Right? So when I take the limit here as s goes to 0, I can distribute it in the numerator, in the denominator. So the denominator as s goes to 0 is alpha, and the numerator limit as s goes to 0 is 0. Therefore, the outcome is in fact 0. And here it is just 0 because there is an s here, this is some constant, and this becomes alpha. So basically the limit here is 0. So what have we shown is that x1, yeah, let's see, right? Yeah. What we have shown is that x1 in fact goes to 0 as t goes to infinity, and that's what by final value theorem. Further, we already know p goes to 0 as t goes to infinity, and p is x2 plus alpha x1. Now, if I take limit on both sides of this, yeah, so if I take limit as t goes to infinity on both sides of this, what do I know? I know that this guy is going to 0. I know this guy is going to 0. Therefore, x2 has to go to 0 as t goes to infinity. All right. There is no two ways about that. Right. So what have we been able to show? We've been able to show that both x1 and x2, there are a couple of things. One is we've been able to show that both x1 and x2 go to 0. Okay. Now, what about boundedness? It's not mentioned here, yeah, but it's also important for our trajectories or our states to remain bounded. Okay. Now, we can do this in two separate ways. I mean, you can choose another Lyapunov function, which is say v bar equals half the same thing as before, k1 x1 square plus x2 square, and we have v bar dot is minus k2 x2 square from this dynamics, right? Just by substituting for the dynamics of the spring mass damper from the previous example, I know that this is exactly what I get, and this is less than equal to 0, and this will immediately imply that x1, x2 uniformly stable at the origin. Okay, so stability can be obtained if you want by this earlier Lyapunov candidate, which is actually a Lyapunov. So I don't have to worry about stability, that was already given to me. But this particular Lyapunov-like construction actually gave me convergence, right? I can claim that x1, x2 go to 0 as t goes to infinity. So I even got my nice asymptotic convergence. All right, great, great. So what we want to do is we want to use the same idea for the adaptive control problem, right? So we already had this sort of a control, and we already had the original dynamics, and of course we had the error dynamics, which was exactly like this. And now instead of choosing k1 e1 squared plus e2 squared, we choose this as a Lyapunov function, or a I will not call it Lyapunov function, but the Lyapunov like function. It is the Lyapunov like function. It is not a Lyapunov function. I'll use this. Yeah, because this is not a positive definite quantity. All right, great. And now we again take the time derivative, just like before. So I get e2 plus alpha e1, e2 dot plus alpha e1 dot, and this quantity just moves. So this guy just remains as it is all through. Okay, because we are yet to choose the theta hat dot. So we choose the theta hat dot every time by taking the Lyapunov candidate or a Lyapunov like function. And from the derivative, we try to choose the theta hat dot so that v is at least negative semi-definite. So v dot is at least negative semi-definite. Right? That's really the idea. So again, we substitute for e2 dot and e1 dot. E1 dot is just e2, and e2 dot is this entire thing. Yeah. So wait a second, this is not correct. E2 dot is in fact plus theta tilde of this entire. Okay. So this is what is e2 dot. Okay. And then what do? We again, if you notice, I still get minus k2 minus alpha here. So I take this minus k2 minus alpha common, and I get e2 plus alpha e1 as it is. And the second term, yeah, we choose by appropriate choice of alpha. Yeah, and with k2 greater than alpha, you will get this sort of term. But if you're confused, you can simply write this as minus k2 minus alpha e2 plus alpha e1. This is the same calculation as before. E2 plus k1 over k2 minus alpha e1. Okay, that is what becomes of all these terms. Yeah, except for this theta tilde term. Yeah, so everything except the theta tilde term becomes this. Yeah. So therefore, if we choose k2 greater than alpha and alpha equal to this guy, we will get here. So these terms become this. Yeah, great. And the theta tilde term, we club the two theta tilde terms together. So I take the theta tilde common, yeah, here, and I get e2 plus alpha e1 times f, right? And here I get theta hat dot over sigma. So now notice that we have to choose a different update law. Yeah, the update law here is now this guy. Earlier, if you notice with the previous Lyapunov candidate, the theta hat dot only contained the e2. Okay, but now it has e2 and alpha e1 both. Has e2 and alpha e1 both. Okay, so that's what. And of course, I mean, there we use the gamma for the adaptation gain. Here you use the sigma. That's fine. Yeah. So of course, sigma is also some positive adaptation gain. So that shows up here. So once we choose that, this term essentially vanishes, and we are left with this guy. Okay, this is also negative semi-definite. Yeah, remember, we did not do any new magic. We did not. So what happens is that the v dot is again the same as what you have in the non-adaptive case, even though the v may have started different. Okay, so this is still the same negative semi-definite v dot. Okay, but what do we know now? Yeah, so here the steps are slightly different. Whatever I had, I had said here that this step is not required and this step is not required, but now we will require these steps. We will. Yeah, why? Because this is not v anymore. The right hand side is not v anymore. Yeah, v contained also the theta tilde squared. Okay, so I cannot use directly the expression for v. So that's what we say. Hence, we won't be write v dot as minus gamma v as in the known parameter case. So we use signal chasing arguments. So what is it? Uh, so this is where we use the earlier arguments. We know that I'm going to write those here, to be honest, yeah, because we said we don't need that. Yeah. So I will write these steps A, B, and C. So what is step A? V infinity. So V greater than equal to 0, V dot less than equal to 0 implies V infinity exists plus finite. Then the second step is that E2 plus alpha E1 and theta tilde are both bounded. Yeah, because that is in the V. Yeah, and V is non-increasing. Therefore, both E2 plus alpha E1 and theta tilde are bounded. The third step is E2 plus alpha E1 is L2. Why? That can be obtained by integrating this thing from 0 to infinity. And I can do this because V infinity exists and is finite. And we just showed that. And further, finally, we can write that E2 plus alpha E1, the derivative of that is also bounded. Yeah. How? Just compute the derivative. E2 dot plus alpha E1 dot. In fact, it is exactly this guy here inside the bracket. This is E2 dot plus alpha E1 dot. And everything here, E1, well, I mean, after taking this K2 minus alpha common, you will get, and with this sort of a choice, essentially you will have E2 plus alpha E1, the derivative will be from here. It will be, let's see, E2, wait a second. It is minus K2 minus alpha times E2 plus alpha E1 plus 1 over K2 minus, yeah, plus 1 over K2 minus alpha theta tilde F. Yeah, so this is what we will have. And so now I know that E2 plus alpha E1 is bounded, theta tilde is bounded. If I assume boundedness on F, I have also that the derivative is bounded. Okay. Therefore, the derivative is bounded. So simply by the Babolat's, the corollary to the Babolat's lemma, I can claim this. E2 plus alpha E1 goes to 0 as t goes to infinity. Okay. And I also know that E2 plus alpha E1 is bounded. So I have the exact same things, right? Okay. So I have the exact same thing as before. Yeah, so now I do the same, I can do the same steps, right? I can say the same steps, right? So what do I know? Suppose I define P of t as E2t plus alpha E1t. I know that P of t belongs to L infinity, and I know that limit as t goes to infinity, P of t is identically 0. Okay, excellent. And I also know that P of t can also be written as E1 dot t plus alpha E1 t. Okay, then I can use the same final value theorem arguments, right, by taking Laplace transform here. So this is PS S E1S minus E1 0 plus alpha E1 S, and so I will get E1 S as S E1 S as S E1 0 over S plus alpha plus S times PS divided by S plus alpha. Okay, so if I take the limit as S goes to 0 on both sides, I know that this is going to 0, I know that this is going to 0. So basically I have this is equal to 0. Yeah, so which means that implies that E1 is going to 0 as t goes to infinity, and because p is also going to 0 and p is E2 plus alpha E1, so I also have that E2 is going to 0 as t goes to infinity. And that's exactly what we want. Okay, that is exactly what we want for the adaptive case. All right, it's exactly what we want for the adaptive case. So notice that there was a change in how I chose the v function, which is now a Lyapunov-like function. And there was, of course, a change in how we update theta hat dot because we changed the v, right? As soon as you change the v, remember that the update law was always obtained by computing the v dot and trying to make it negative semi-definite. Yeah, and so it's obvious that if I change the v, the choice of v, the choice of the update law, of course, changes. Yeah. So it's not like I'm getting conversions of the tracking errors to 0 for free. Yeah, because this is just analysis, right? After all, choosing a V and doing derivative and substituting dynamics is the analysis. One might ask, what did I actually change in the controller? So I did. The controller remained exactly the same, but the update for the theta hat changed. And with this change in the update, using the same sort of steps that I did for the known case using this, uh, you know, Ortega construction, I could actually show that both E1 and E2 are now going to go to 0 as t goes to infinity. Right? By the way, this sort of proof that we did that if E1 dot plus alpha E1 goes to 0 as t goes to infinity, this proof can also be done in the time domain. Okay, it's not impossible to do this proof in the time domain. Yeah, because this is a nice exponential decay, nice system with this is a nice exponential decaying system with a bounded time or bounded vanishing perturbation. Yeah, so this sort of analysis can also be done. Yeah, I mean, I would strongly encourage you to look at how to prove the same thing without the final value theorem and going to the S domain or the Laplace domain. Yeah, I would strongly urge you to try to do this simply by directly integrating this system. Yeah, because this is just a bounded vanishing perturbation on a exponentially stable system. All right, excellent. So that's great. So this uh, sort of brings us to the end of this week's lectures, and we have done rather interesting things. We have seen our first set of adaptive control problems. We saw that how to do the first order case, start with the unknown case. Sorry, start with the known case, use certainty equivalence to design a controller for the unknown case, and then come up with an update law using a appropriate Lyapunov candidate function. And we also show how to choose the candidate Lyapunov function. But as soon as we moved to the second order system, we saw that it's not very difficult to hit a detectability obstacle if you end up choosing a non-strict Lyapunov function for the original system. All right, so it's not that complicated or that difficult to get to a detectability obstacle. And then we also saw a means of alleviating the detectability obstacle by choosing what we call the Ortega construction, which is essentially a Lyapunov-like function, which still helps you with the signal chasing analysis for these kind of integrator type systems. So you essentially have an integrator type system. If it was not an integrator type system, this sort of construction may not work. You might need to use a strict Lyapunov construction. But then with this type of Ortega construction, we showed that with the a second order scalar system, we are able to in fact make a nice adaptive control design and show that both the tracking errors go to zero. As always, we don't claim anything on the parameter error. We of course show that it's bounded, but we don't claim anything on whether it is converging or not to the true value. All right. And this of course brings in notions of persistence of excitation. We looked at that for the first order scalar case. We did not look at it for the second order scalar case, but it's similar. You can do a very similar thing for the second order case also, and probably use persistence results that we've discussed before to claim that under rich enough um, trajectories, you will be able to identify the parameters. But how to find the rich enough trajectories? How many frequencies do you need in the trajectory? These are all still uh, heuristics. It's more like trial and error. Yeah. And like we've already discussed, it may not always be possible in a real application to create these arbitrarily oscillating trajectories because you may not want your robot to follow such trajectories. Excellent. So I hope it was a very interesting week 6, interesting excursion into the start of the design process. And so henceforth we will see more and more of the design. So I'm very hopeful that you will be able to pick up tools from here and start applying to these small, tiny problems that all of you are probably already trying to solve in your own, fields of work. Thanks a lot, and I'll see you again soon.